Hello and welcome everyone to another Applied Flow Technology webinar. My name is Nick Vastine with Applied Flow Technology, and today I'm going to be walking you through an introduction to AFT Arrow, our compressible flow modeling tool. We'll start the webinar with a brief introduction, overviewing a lot of the assumptions and applications of AFT Arrow before we build our first model, and in this case we're going to be sizing an orifice to restrict flow. There's really two phases in the modeling process. First, building the model, and then further, how do we analyze and understand the results of our model? There's some other odds and ends that we'll touch on. We'll look at heat transfer effects, and then we'll also touch on sonic choking, a phenomenon typically exclusive to compressible flow. Towards the end of the webinar, we'll touch on other add-on modules, which increase the capabilities of the base product. And then finally, if you are a brand new user, we'll touch on some additional learning resources to continue your learning journey. So AFT Arrow is a software designed for modeling piping and ducting systems, and it's designed for compressible flow. So whether that be a gas stream or steam or a vapor, it's going to consider those compressibility effects. In short, what that means is that your density is no longer fixed. Your density can change with pressure or with temperature. Obviously, that's going to impact your velocity and your pressure losses, and all of these factors are going to contribute to what's your ultimate flow solution. Arrow is a steady state solver. That means that things are not going to vary with time. It's a continuous solution, but we can also use that steady state solver to approximate long transients. So if you have a blowdown event or a tank filling event, we can use that steady state to approximate how much mass is going into a tank over a certain amount of time. We'll touch on that again a little later in the webinar as we go into the add-on modules. As I mentioned, we do consider all of the compressibility effects. That includes also temperature effects. So if you have a completely adiabatic system, you'll still see temperature changes due to things like the Joule-Thomson effect. Further, we can consider additional heat transfer effects, especially if you have solar radiation. That might be dramatic. That might make your fluid expand and change your solution. Sonic choking, again, exclusive to compressible flow, that we'll overview. And then also you can model dynamic mixing. So if you have multiple components, let's say you have a natural gas stream and an air stream, and you're trying to mix them in a particular ratio, you can model that mixing within the software as well. Some common applications. Today we'll look at equipment sizing for an orifice, but you could also size things like compressors or blowers, control valves, relief valves. Again, anything tangential to that piping and hydraulic analysis. As energy efficiency becomes a higher and higher priority for many different companies and for systems, what opportunities can you assess within your model to tweak operation to improve operating efficiency? In the same vein, if you have a physical system that's running into problems, you could build a model and that would indicate any differences, helping in the troubleshooting process. Or if you have a physical system and you're trying to increase throughput or add a new consumer, you can test that out in the software, identifying where you need to make modifications or if the existing system can handle that new capacity. Here are some of the common systems. Most common, I would say, is utilities, especially looking at steam systems, but it's also common in HVAC or natural gas pipelines. Again, anywhere that you have to consider that compressible flow. We also see it commonly in aerospace applications or in hydrogen or in helium as well. To kind of demonstrate the depth of features, again, as an introductory webinar, we can't go to the full depth of a training class. But here are some example models here on the left to highlight some of the features and applications of our software. So these all stem from case studies, which you can find from our website if you're curious. This first case study was a helium cooling loop where they were testing different components for a nuclear fusion reactor. So they were modeling how helium would transmit through these turbo circulators, through these different heaters, heat loss to ambient conditions, how much insulation do you need? Again, modeling that steady state process for testing these different components. This system is a distribution system, I believe, for a natural gas distribution network, where they would have their different distinct consumers, ensuring that they can meet the flow demands of each consumer. And then finally here we have a wastewater application where they were doing wastewater aeration, supplying air to promote the digestion of solids and waste in the wastewater clarification process. So again, the models that we're going to be building today are going to be a lot simpler than the models we see here, but don't take that as a limitation of the software, more so it's a limitation of doing this introduction. So without further ado, we'll take a look at our first model, and here we're going to be sizing an orifice. We have a tank that is higher pressure, and it's going to be driving flow towards this lower pressure tank, where here it's at atmospheric pressure. We're going to be flowing steam, and we want to limit that steam flow to only 2 kilograms per second. So we want to throttle the flow until we've limited it to this 2 kilograms per second flow requirement. Our pipe sizes have been decided already, but this could be something you could test in the software. We're going to be looking at ANSI steel 2-inch piping, and then we want to estimate some additional losses in our pipeline that could represent additional elbows or isolation valves, other components that are going to add frictional losses to this section of the pipe. Rather than do guess and check in different orifice sizes to determine this flow requirement, we're instead going to use a control valve, and that'll tell us the ultimate orifice size, again, streamlining that overall process. So let's jump into the software, and then we'll come back to the presentation to kind of outline where we're going to be building the model and how that process works. So when you first open Arrow, you're greeted by the startup window. Over here on the left, you can open existing models that were previously opened or are example files. You can activate modules, select your fluid, or if you're looking to learn more about the software, we have a collection of resources here on the right. Again, we'll go into these resources in more detail towards the end of the webinar. One thing I will change here is the modeling preferences, where I will set my unit set to be both US and metric with default metric units. You can further filter down these units. You can completely customize them. For example, if you're looking at pressures, if you're looking at especially high pressures, maybe you don't care for inches of water or centimeters of water, millimeters of water, for example. So this can be streamlined further to, again, accommodate the unit set that you are working in, and then we'll see other places where unit flexibility comes in, both in input and during our output process. So here we'll set it to both with metric defaults. You can similarly change things like the language you're working in if you prefer 2D freeform, which we'll work in today, versus an isometric, or set your default pipe material, but in our case, we'll just go with the default settings. We'll remember those preferences, and now we'll start building our model. And we're greeted by the first window we're going to get familiar with, which is the workspace window. So if we jump back to our presentation real quick, the workspace is where we're going to connect all of our pipes and junctions, and it's also where we're going to be defining the majority of our properties. So for example, we have our tank pressures, our tank elevations, all of the characteristics of our pipes. All of that is defined in the workspace. A little later in the webinar, we'll talk about workspace layers and how we can build on top of the workspace for reporting and for visualizing results. But for now, we're just focusing on the model construction aspects. So here back in the software on the left of the workspace, we have our toolbox where we have different junctions that we can use for our model. In our case, we're going to drag a tank onto the workspace. We'll drag our control valve, which we're going to be using to size our orifice, and then we can drag another tank onto the workspace. The junctions can obviously be much more complex. You can capture heat exchangers, for example, and all of the different heat rates and models of a heat exchanger to consider. We'll touch on that a little later. Compressors or fans operating on a curve or on a compressor map. Relief valves, orifices, venturis, sprays. Again, there's a lot of different options to capture either hydraulic losses, changes in temperature, or changes in pressure within a specific model. So here we have our 3 junctions that we've added in, and now we need to connect them with pipes. If we double click this pipe drawing tool here in the upper left, we can drag and drop and connect these different pipes or these different junctions. Note that how the model is laid out is not going to necessarily dictate your results. For example, if I increase the elevation of this tank, let's say visually it looks like it's going uphill, this does not impact my specifications or the parameters that I would input. In the same vein, if I put it down here, it's not going to suddenly say, oh, now it's flowing downhill. If I bring it closer to the control valve, that doesn't shorten my pipe. In the same way, if I make it very long, my pipe is no longer suddenly longer. For the most part, the workspace is a visual representation. Some things do depend on this visual representation. For example, in our control valve, we have to have a flow coming in and a flow coming out. If I were to change this pipe direction, this would be an invalid solution. So here, we'll change it back as we flow from our high pressure through our control valve to our low pressure tank. Now we can begin specifying the parameters for each of these junctions. To do so, we're going to double click on a junction and that'll open the properties window. And all of the required information is highlighted in light blue. So the elevation, which is required, our pressure, which if you remember was 16 bar gauge, and our temperature was 260 degrees Celsius. We'll define our fluid a little later, but we'll see that's also required input. If we wanted to name our junctions, we can also do so here. If I name this the inlet tank, that makes it very easy to search later. So it might be valuable to name things like control valves or consumers or compressors. So that way, as your model gets more and more complex, you can very quickly find the junction that you're looking for. We'll do the same specification for our outlet tank. So we'll call this the outlet tank, where here we are at 0 bar G and then 260 degrees Celsius. Similar to the naming, you can also include notes on the junction. Let's say this is discharge tank, let's call it Denver 001. And these notes are too searchable. So if I search for Denver, it'll bring up that outlet tank. So if you have a spec sheet of information, maybe you have equipment tags, you can put that into the notes or into the name of the junction to make it easily searchable in the future. So we've defined our two tanks. We can now go ahead and define our control valve. If we double click the control valve, again, everything that's required is highlighted in light blue. The control valve can have a lot of input, so we'll keep things very high level for now. We'll set it to a flow control valve, so we're controlling the flow rate from our upper tank, our inlet tank to our outlet tank. And we want to set that to a mass flow rate of 2 kilograms per second. If we click OK, now we have fully defined our 3 junctions. One way that we can check that everything is fully defined is whether or not we can run our model. Here we can see it has a little stop sign saying we need to further specify the model before we can run. And we also have this status light here in the lower right telling us we need to further specify the model before we can run and generate our output. If we click on the status light, here in what's called the analysis setup window, which we can also access from this button up here, everything with an exclamation point indicates that we need further specification before we can run our model. So in our pipes and junctions, here we can see our control valve, our outlet tanks. These technically still need the fluid to be fully defined. And for our pipes, we still require the length, inner diameter, and the roughness. Another way you can visualize this is with this status light up here. And now anything highlighted in red is indicating to the user you need further specification to run your model. So let's go into the pipes. Again, double clicking on the object to open the properties window. And here is where we could specify things like our inner diameter. So if we wanted to model a 2-inch pipe, that's 3 meters long, and maybe we estimate a roughness of 0.0001 centimeters. Obviously, that manual input can be a lot of information for the user, and also it can be very error prone. Maybe I misspecify the units and now my solution is invalid. So one way that we try to resolve that is AFT does provide a pipe material database for you. And these are generally customary sizes or sizes consistent with standards. For example, the ANSI steel that we'll look at today, it includes a full range of different pipe sizes, and within those pipe sizes also a range of schedules. So ultimately we'll come back to this 2-inch standard Schedule 40 piping. Note that in compressible flow, it's also common to flow through ducts rather than purely cylindrical pipes. You can either user specify that information as a rectangular duct, specifying the height and the width, or there are some customary databases for rectangular ducts within these provided databases. So here we look at a 10-inch by 4-inch, and again, a range of different gauges, which could impact the size, or I believe it can impact the roughness as well. So here we will go ahead and define ANSI steel 2-inch, and again, highlighted in light blue is our required length specification. If we click OK, check our status light, we can now see that pipe 1 is fully defined. We'll now move on to pipe 2. One thing that we do for convenience for the user is we bring over the pipe size as you're specifying each pipe in sequence in a pipeline. So I only need to specify the length to fully define this pipe. Note, however, we want to consider additional fittings and losses. Let's say that there's elbows in the system or isolation valves, and we want to capture those fittings and losses within our model. So if we go to this fittings and losses tab, and down here on the right, specify fittings and losses, this brings up the fittings and losses library, where we've provided things like bends, valves, check valves, orifices, area changes from some general hydraulic sources, Crane, Idle Check, and Miller. You can also user specify your own fittings and losses. Let's say you have a series of valves that you're always going to be using in your model. You can add those in as fittings and losses, again, ensuring that you're making consistent input, especially if you're sharing models across engineers or if you are using the same equipment across multiple models. So here, for example, if we had 10 elbows in the 6-meter pipe, which is a very bendy pipe, we would have our K factor of 5.66, and we would account for that additional pressure loss from those various elbows. Here, in our case, we're just going to estimate an additional K factor of 1. And if we click OK, we can see a few things have changed. We now are indicating in the pipe properties, this pipe has fittings and losses. And if we hit OK, we can see on our workspace, this pipe has an ampersand indicating there's more than just the pipe losses through this pipe. So now if we double check our undefined objects, we can see we only have the 2 tanks undefined because we have not yet defined our fluid. So let's go ahead and define our fluid now, which we can access again from the analysis setup window, or you can go directly to the fluid clicking on this little beaker. Here in the fluid, there's a range of different fluid databases. So odds are we have a component that's representative of what you're trying to model, especially on the process side. And if need be, you can also create mixtures. Let's say you have a natural gas mixture that's primarily methane with some amounts of ethane and other hydrocarbons. You can consider that either on a mass fraction or mole fraction, and it'll again consider all of those thermodynamic effects, or in some cases, how do you model the dynamic mixing? So mixtures, you have to use the ChemPack database, which is an optional add-on, or the default provided NIST RefProp fluid database. In our case, we're going to use AFT standard, and we're going to use our steam model, where all of these different fluids have just been curve fit to run efficiently with our backend solver. You can also user specify your own fluids or use ASME steam tables, again, if you require kind of additional resolution or you need kind of further confidence to say, no, I'm referencing steam tables to justify where your fluid properties came from. So we will default to steam. And if we click OK, we can now see that a few things have changed. The status light is still on, but all of our junctions are ready to go. The status light down here is now green as well, and we no longer have that limitation on running our model. So that's everything regarding the workspace. Again, we'll come back to it to discuss this workspace layers feature a little later in the webinar. But for now, think of the workspace as where we add our different junctions, connect them with our piping, and then specify all of the properties for our model. The next thing we'll take a look at before we run our model is model data. This is all tabulated data where we can double check our input and also where we can spot check or modify different aspects of our system. So if we pull up the model data tab, and we'll zoom in quite a bit to make it easier to see, here we can check our lengths very easily. For example, all of them are in meters, none of them are in feet or in miles. That could be a common troubleshooting issue. And if we wanted to double check our nominal size, we can also see that here as well. We can double check other things like our tank pressures, where here we see our elevations are still 0 and we have our 16 and 0 bar G specifications. Anywhere that you see kind of tabulated information, you'll see it in model data and we'll also see it in output. That can be easily extracted into Excel if you need to provide a more tabular report, or if you need to perform additional calculations in the case of output, for example. Other things, it will show things like your notes if you have your tags in here, and then it can also tell you things like your fluid. So here we're looking at steam, and it provides that temperature range of where is this fluid property valid. Another feature we'll show is you can also rearrange these windows. So here, if I put model data on its own window, that also makes it easy to spot check things like my piping. So here I can see pipe 1 is 3 meters, pipe 2 is 6 meters. Alternatively, you can use what's called the inspect feature. If you hold right click on an object, you can see the input, and also when we run the model, you can inspect those objects to double check the output as well. So you can check things like pipes. Here we can see that our outlet tank pressure is still 0 bar G. One other feature with these windows, again, you can place this freely. You can also drag it off onto another monitor. If you have a dual monitor setup, that can be convenient, especially as your models get more and more large and more complex. So that is, in a nutshell, how we build our model, again, reviewing the workspace window and the model data window. While we went ahead and built our model from scratch, you can also import models from other sources. Obviously, that'll save time and also reduce any input error if you've already confirmed your model in another application. So this example comes from a case study where they were looking at a 11-story HVAC system. They had their model in Navisworks and they were able to import it into another one of our products, AFT Impulse. Though it is a different product, the import process is going to be consistent across all of our applications. Also note that AFT files can be opened in other AFT applications. For example, if you do a steady state compressible analysis in AFT Arrow, and then you need to perform a transient analysis in our transient software AFT Extreme, you can bring that model in fully into that other application. You don't need to rebuild that model from scratch. To touch on the import options in a little more detail, we have 4 types of files that we can import, again, in addition to those AFT files, whether that be a piping component file, commonly generated from CAD drawings, a Caesar2 neutral file, more common in pipe stress analysis, GIS shapefiles, and EPANet as well. All of those are accessed from that file menu, import piping layout, and then you can select the file and it'll provide a preview. We have another webinar that goes into much more detail on the import process. Again, this is much more an introduction. For the sake of brevity, we can't go into depth of all of these different features. Let's talk a little bit more about fluids. So we defined our fluid as steam. And in review, we saw how we can define predefined mixtures using either the default provided RefProp database or the optional for purchase ChemPack database, or you can user specify your own fluid if need be, whether that's extracted from a process simulator, something like ChemCAD or Aspen Plus. You can also model various equations of state. I didn't show this in the software, but you can change the equation of state depending on what you're modeling. However, in general, I would say Redlich-Kwong, which is our default equation of state for most of our fluids. Typically, you don't need to modify this to improve things like convergence or depending on the fluid of your model. Usually that's provided for you. As we will see when we run our model, we'll consider heat transfer effects, including the Joule-Thomson heating and cooling effects, whether it's hydrogen and helium, and you see Joule-Thomson heating, or adiabatic cooling for most other gaseous fluids. Again, this will also apply to mixtures. So if you have a natural gas mixture or a mixture of other process fluids or user-specified fluids, we can consider how is the fluid properties going to change with temperature as well. One thing I didn't mention is you can also model different fluids in different pipes or different sections of the model. let's say you're modeling the steam side of a system and then also the process side of the system, you can distinguish those different fluids in those different sections of the model. And then also, as we talked about, you can model dynamic mixing of your different fluids. If you had, again, in the example, natural gas mixing with air before feeding to a combustion chamber. Note, however, this has an asterisk, and you will require using either the NIST RefProp database or the ChemPact database for this dynamic mixing capability. I believe this is the last thing we'll touch on in terms of building the first model, and that is libraries, which we saw a few different examples of while building our model. Pipe materials, it's probably the most common application where we looked at our ANSI steel 2-inch standard schedule piping. While we do provide a wide range of different pipe materials, you can always customize these databases and add your own pipe material database, especially if it's more customary or consistent with the systems that you're modeling. Fittings and losses, we saw all of the different fittings for bends, orifices, isolation valves, check valves, things of that nature, which again, we provide from customary sources from those hydraulic handbooks, but you can always add your own custom K factors for fittings that you're going to come back to over and over again. Fluids, as we saw, we provide a few different databases, but again, you can save your own user-specified fluid database or fluid information that you can then call in different models or to capture for your own distinct system. One thing we didn't touch on is how you can save junctions to a library. Let's say that we have a common valve that we're going to be constantly specifying or a common compressor we're using all the time. You can save that to a library. That makes it much more convenient to call in the future as you're building other models. And then finally, as we look at heat transfer analysis a little bit later in the presentation, you can also adjust things like the insulation on your piping. As I mentioned, most of these libraries are going to come with predefined information, but all of them can be further customized as you see fit and as you need. These libraries are also valuable because if you invest the time in them up front, it's very easy to share those across different users or across models and different projects. You can host them on a server. And again, the intent of having this standard library of input is you're going to standardize that input that reduces any input error, and then obviously it's going to save you engineering time instead of always looking up the same K-factor losses. So in summary, models are made up of different objects, both pipes and junctions, where those junctions can represent all sorts of different things within your model. It can be pressure loss, like a valve or an orifice. It could be pressure gain, like a compressor or a fan or a blower. It can be different mixing points. It can react to your changing system conditions. For example, if your compressor is operating on a curve, if you change the flow rate, the amount of head or pressure that the compressor has to add will change. Or it may be a relief valve that opens or a check valve that closes. Again, think of it as a system approach to analyzing and designing your hydraulic system. We saw in the workspace where we connect all of our different objects and we define all of our parameters. Again, the arrangement of the model will not impact your results. However, how the objects are connected will impact those results. As we saw with the control valve, if we have 2 points coming into our control valve, that's going to be an unacceptable solution, but we can rearrange them, space out our piping, space out our components however we please. We saw how model data is useful to double check our input, especially if you are troubleshooting and double checking another engineer's work before doing your runs and doing your analysis. And then finally, as we saw, there's a lot of different ways to see what needs to be defined for the object to run. So we saw the light blue highlighting, we saw the status light in the bottom right, and we saw those undefined objects in analysis setup or from the workspace, again, directing the user what needs to be defined in order to run and generate results. So we've done everything to build our first model. Now we can run our model and perform our analysis, and we'll start by reviewing our output, which is tabulated information. It's useful if we need to pull a specific number or if we're sizing equipment and we need, again, exact parameters to bring to a manufacturer. And also output, it will indicate any warnings or cautions. For example, here in this model, we can see that it's sonic choking in 3 different areas, which again, sonic choking we'll touch on a little later in the presentation. So back in the software, if you remember, the status light down here on the right is now green, and we have no limitation on running our model. If we go to run our model, it'll ask us to save our file. Here, I'll just call this our orifice sizing example. We save, and because it's such a simple model, it runs very efficiently and solves in only 2 iterations. Here on the solution progress window, we have a few options. We can go directly to output, back to the workspace, or to our graph results. And again, we'll go through these each in turn. So we'll start first with our output. And as you can see, it looks very similar to model data as we saw before, but now we're looking at the results of the model. So we can see here, we're meeting our mass flow rate requirement of 2 kilograms per second. And we can also start to see the compressibility effects that we're capturing in AFT Arrow. So our velocity in is no longer equal to our velocity out. And we can also see how close we are to that sonic choking limit based on our Mach number. We can see how from pipe 1 to pipe 2, when we go through our control valve, we can see a pretty dramatic increase in our velocity. Again, because we see pressure loss across this valve, the fluid then expands, it increases the velocity going through the remaining piping. So here, if we wanted to check other things like our valve, here we can see we're creating almost 5 bar of pressure loss across this control valve. We can see the equivalent K factor, and if we were sizing this control valve, it'll provide us an estimated CV. So let's dive into output in a little bit more detail. Again, as we saw with model data, any information you see like this, you can very easily extract into Excel if you needed to perform additional calculations. But many of the parameters or calculations you might want to calculate likely exist within the software already. So let's say that we have our default units in meters per second and we needed to report it in feet per second for an American client, for example. While we could extract this information, perform a unit conversion, instead we can just update the units from output. So if I double click the header, here I can select the different units very easily, and now I can compare in feet per second instead. And again, any of these parameters you can double click to quickly change the units you're reporting in. If I wanted to add additional variables, let's say I want to show velocity in feet per second, but also I need to report it in meters per second because I'm working internationally and some of my engineers use metric, some of my engineers use English units. If I click this output control button here in the upper left, this controls what's shown in the output. It's a very intuitive name. And here we can see things from our pipe reporting. So we see the name of the pipe reported there, the mass flow rate in kilograms per second reported here, our velocity in, which we can very easily change back to meters per second if we need, so on and so forth, again, showing all of the different variables reported here in the pipe output. So we can add additional variables here on the left, and you can also add redundant variables. So let's say I want to show the velocity at the inlet. I can add that to my output control. I can rearrange it to bring it next to my velocity inlet, and I can change my units to the feet per second that I need. If I click OK, I can now see I'm reporting both of those variables. Again, much more convenient. I don't need to do any manual conversion or manual calculation. So the next thing we're going to show is, again, for our orifice sizing example. Remember, it's not going to be a flow control valve in the final created installed system. We're just using this control valve to size what's going to become an orifice. So here, if we wanted to size our control valve, we're provided with a CV, or from output control. Now, instead of modifying the pipes down here, we can instead modify the output for our valves, editing this valve summary tab up here. And I can add things like our equivalent orifice area or our equivalent orifice diameter. And now if I click OK, I can take this orifice diameter, I can send it to the machine shop or to a manufacturer, and ideally it should perform exactly the same as this control valve does in this particular setup. We'll demonstrate that capability a little bit later as we get into scenarios, but again, the main gist of output is it's all of this tabular information we can extract and modify, including a lot of additional parameters that we can add to avoid doing manual calculations or conversions to different units. Again, as an introduction, it's unfortunate because there's so many other features that we can go through. We saw how in output control, we can add and remove our parameters and adjust our unit flexibility. We can also show multi-scenario output, so we'll get into scenarios a little later in the presentation, but how can we compare the results from those different cases we're analyzing? We can automate the export of this analysis to Excel, and then we can also add things like design alerts that indicate, hey, maybe I have a maximum velocity for these different pipes. It'll automatically indicate as an error or as a warning message, you invalidated this design requirement in pipe 2, 3, 4, 5. For example. Again, these are some keywords that you can look for in our documentation, and those will go into those features in much more detail than I can here. Or if you enjoy these webinars, stick around, and I'm sure that a lot of these features come up naturally as we give them. So that is our output information. Next, we'll take a look at our graph results, which is very valuable to see how different parameters are interacting with one another, especially in compressible flow. So we can create things like fan and compressor versus system curves. We won't do that in today's example. Profile graphs, which show how do different variables change along the length of a pipe. And then you can also show transient graphs or how things change over time if you use the add-on module XTS. We'll also show how we can save those graph list items as templates. So if we make other changes to our analysis, we can very quickly reload those graphs. So now back to the software. Instead of the output window, we'll now go to graph results, where we do include a graph guide that walk you through the different steps of creating these graphs. So if we click quick and simple, here you can select a profile graph and it'll indicate to you, here's the steps you need to take to create this type of graph. So here in our profile graph, we're going to select the different pipes that we want to show. Here we're only showing pipe 1 and 2. So I want to see how are my variables changing from my inlet tank all the way to my discharge tank. And we can graph things like the pressure, for example. So if we recombine all of our windows together, here in graph results, we see the gradual decrease in pressure as we get flow through the piping and we have those frictional losses. We see the very dramatic decrease in pressure as we go through the control valve, which is really throttling our system. Again, creating a high pressure loss to restrict our flow. And then here we see, again, that increase in pressure loss due to friction, and we see it starts to increase more and more over time. So that's kind of an odd phenomenon, not something you would expect in incompressible flow. Let's now look at our velocity. So if we add a variable, I'll add velocity to the plot. And now we can see, well, maybe the pressure loss, getting more and more steep towards the end starts to make sense when we look at our velocity. So as the pressure decreases, we see our velocities also increasing. At that very high pressure loss, our fluid will also expand and have a lower density, therefore it needs to flow faster. And the faster and faster it flows, the higher and higher pressure losses are created. So before we show more of the graph features, let's actually jump ahead and let's talk about some of the challenges of compressible flow, since now we're getting into some of the analysis. So here we have, again, a very similar system, our inlet tank, our discharge tank flowing through an orifice. If we think about how we're solving this system, the flow rate going from the inlet to the discharge informs our pressure drop. The pressure drop with pressure within the pipe determines how dense our fluid is. The less pressure, the less dense our fluid. That informs our velocity, that informs our pressure drop, which informs our density, which informs our flow rate, so on and so forth, et cetera, et cetera. Temperature is also going to have an effect if we're heating the pipe up or if we're cooling it down. That too will impact things like our pressure in the pipe, which impacts our flow rate, our density, our pressure, our flow rate, our density, et cetera. So similar to what we just looked at, we can see that pressure loss from friction, that dramatic decrease due to, in this case, the orifice, and then that more dramatic increase in pressure loss as we increase our velocity more and more. So how do we capture these compressibility effects within Arrow? We use what's called a march method, where we march along the length of the pipe so that we can calculate intermediate properties. So as we transmit through P1, we can say, okay, we see this amount of pressure loss. What's our new density at this point? What's our new temperature? How do all these variables interact? There's two ways that we can approach it. One is a length march, where we'll just split a pipe, for example, into two sections. So I calculate it at the inlet, at the middle, and at the discharge. However, as you get faster and faster flow, if we were to apply the same calculation, we might only have 1 point here, 1 point here, 1 point here. Obviously, we're missing all of the resolution of this accelerating flow. So instead of a length march, we can also do what's called a Mach march, where we increase the number of calculation points in the middle of the pipe depending on how fast it's going. So if we jump back into the software, if I use this little crosshair tool, we can actually see where we're calculating each of those intermediate points. So at first, to be more efficient, we calculate 3 sections for this first pipe, the inlet, the middle, and the outlet. Because it's very linear, because there's not a lot of pressure loss or change in velocity, it's probably a good representation of the system. But as we start accelerating in flow, you can see here, each of these little annotations is a point that we've calculated, and we start to calculate more and more, especially as we approach this sonic choking condition. So by adding all of these intermediate calculations, that's how we're capturing those compressibility effects so that we can calculate those intermediate fluid properties. Again, if you're curious, we have other webinars that go into much more detail about the solution control aspects, but this is really the first introduction of how are we capturing that compressible flow effects. So back on the graph, again, this is more of a showcase of the different features now. We can also showcase the same or 2 different parameters on the same plot. Let's say I want to see pressure on one axis and velocity on another axis. If I select this second parameter, I can click this right arrow to make it our secondary y-axis, and now I can cross-plot both of them on the same graph. If I wanted to, I could right-click and copy the graph image. Maybe I'll paste that directly into a report, or I can copy the XY data and again, paste that directly into Excel. So you can add a lot more variables. Let's say we want to show our temperature, our stagnation temperature, and then also let's say Reynolds number, sure. And it'll add these plots stacked on top of one another. You can then rearrange things like the font size or change the scaling. Let's say here we want to start from 250, maybe 200 instead. That way we can zoom into it, or you can zoom into the plots directly to get more precise in your analysis. If I right-click the graph and add the graph to a list, we'll call this our profile graph. Now, if I make any other changes to our system, I could very easily reload my graph, and it saves it exactly how I had it set up. So let's say I start changing parameters and I screw it up. If I reload my graph, again, it's exactly how I had it set up before. So that is graph results. Again, much more an overview of the capabilities rather than an in-depth tutorial, just bringing awareness to how you can modify and change these parameters. So now let's jump back to the graph results and let's talk about how we can further enhance them. So we saw both dual y-axis graphs and stacked graphs. So dual y-axis, that could be different parameters, or here in this example, we have bar G on the right and PSIG on the left. You can graph multi-scenarios. Again, we'll touch on scenarios here in a moment. You can also add annotations, maybe labeling where your control valve or your orifice is. And then you can also further customize the formatting if you wanted to rename things like your legend, if you wanted to change the scaling or add more intermediate points for major and minor grid lines, for example, or changing things like how the lines are colored or if they're dashed, again, things like that. The way I like to phrase it is you want to make your graphs report ready from the software. You don't need to bring them into Excel and do that additional step. You can just have your model, save them as graphless items, and very quickly generate those graphs to paste into your reports. So before we touch on scenarios, next we'll touch on workspace layers. If you are a legacy AFT user, this is going to replace those visual report features. And it's a way to display things like our input and our output parameters next to the objects in the model. So our velocities, for example, for each of these pipes, or our pressures for each of these tanks. And we can also use it to create color maps. Maybe we want to color code things like a maximum velocity that'll automatically flag us if our velocity is too high in any pipes. And we can also use it to control object visibility and style. So let's say we have a very complex system. Maybe we can color code it to show hot lines versus cold return lines, or maybe we want to isolate a subsystem and hide the rest of it while we're giving a presentation. Again, a lot more flexibility is added by workspace layers, which again replace visual report. So this is a feature new to Arrow 10. If you go to the visual report tab, we'll show you, visual report no longer exists, and here's some additional documentation you can refer to. Where here on the workspace, we're going to be working in this workspace layers tab. So by default, all the objects are included on this all objects layer. If I change the visibility of this layer, I can hide all the objects, but obviously my specifications and all of my connections are still in place in the model. Layers can be great, again, for changing the style of things. Let's say I wanted to analyze my two tanks, or I wanted to emphasize them in my model. I can select the two tanks, click this plus button for a new layer, and I can create it from my workspace selections. So I'm going to create a layer that only contains my selection of these two tanks. Let's call them tanks. Now, if I turn off the all objects layer, I can see that this tanks layer still has my two tanks visible. If I go ahead and modify the tanks, here I can do things like change the size of the tank, or I could change the color. Let's say I change it to Indian red, for example. And it'll still preserve my original model. I can now just turn this layer on and off for visibility's sake. So from a style perspective, it can be useful. I would argue it's a bit more useful for checking things like your model input or reviewing your model output. So here I've selected my two pipes, and let's create a layer from our workspace selection, so only including the two pipes we have selected, and let's call this our pipe input layer. So now if I go into the pipe input, again, we could change things like the visibility settings, but I'm going to focus on this pipe parameters option. So if I'm double checking my pipe input, maybe I want to show the pipe length, which I can search and add. And now I can see on the workspace, right next to the pipes I'm assessing, here are the lengths. So I can spot check piece by piece how long are my pipes. Maybe I also want to check things like my nominal size. And again, I can confirm that both are 2 inches in diameter. So I can very quickly hide those different layers, and I'm back to just my model, and I can go back and reactivate them if I need to, again, spot check that analysis. It's not limited to input. Any of those parameters that you saw in output can be brought into a workspace layer. So let's say we want to show our velocity for our inlet for our pipes. And again, you can show a mix of your input parameters or your output parameters. You can do the same thing for junctions. So if you wanted to show pressures or DP across a valve, again, all of that can be further customized as layers. So we'll go ahead and we'll hide our different layers, we'll bring our labels back over. And the last thing that we'll show related to layers is a color map. So here I'll click new layer and I'll select color map from the menu. And here, let's say we want to plot our maximum velocity. So the color map is a little different from the standard layers because when the color map is on, it supersedes a lot of the other styles that you would have added to pipes, for example. Like if I had a hot line and a cold line, the point of a color map is to color code the pipes, so it's going to overwrite those style changes I would have made in these standard layers. Here the color map, by default, we look at pressure static maximum. Here we can see it's a much lower pressure in pipe 2. somewhere between 10 and 12 bar. And here in pipe 1, it's somewhere between 16 and 18. So as you can imagine, if we look at something like velocity instead, let's say we look at the velocity at the outlet, which is going to be typically where it's going to be flowing the fastest. Maybe if we had a maximum velocity requirement of 450, all of our pipes that are red in our system now indicate, hey, we've invalidated this design requirement. Or you can see at a glance, maybe you have a distribution system. Am I getting adequate flow rates to each of my various consumers? All of these settings can be changed. So if I wanted to increase it to 500 instead, again, it can be user modified, spaced out depending on however you want, or you can color code it however you please as well. So that is workspace layers in a nutshell. We saw how we can use it to quickly double check our model input and our output, reviewing things like our length and nominal sizes. We can print them and just take a screenshot of them to include in our engineering reports instead of a table of data. You can stylize different subsystems or visually isolate them by creating a layer with only those objects on it and showing that layer. And then also you can set up your different types of reports. Maybe you have one for velocity, one for your pressure check, one for your temperatures, which you can turn on and off depending on what step of analysis you're doing. So that's really everything from the primary window perspective. Again, workspace and model data for building your model, output, graph results, and workspace layers for analyzing your output. Excuse me. Next thing that we'll touch on is scenarios. So scenarios are different variations of our base system to quickly evaluate changes. I like to think of it as a way to quickly experiment with your model without worrying about destroying all of the work that you've done already. So here, for example, we have a model where we have a main supply. Sometimes flow goes to tank A, sometimes flow goes to tank B. We'd want to consider those two cases. Maybe we're sizing the system and we want to evaluate a range of pipe sizes for all of these pipes. We could also assess those in scenarios. And maybe we have different fluids that we're moving, sometimes to tank A, sometimes to tank B as well. So we can use what we call the scenario manager to organize all of those different design cases, all of those different operating points. So that way we have the most comprehensive analysis to inform our decision making. So the way to think about it is scenarios are duplicates of the models, where characteristics in the children scenarios, so the kind of descendants from these upper scenarios, are all inherited from our parent scenario. So let's go through an example. Let me turn off the workspace layer. And here we're on the scenario manager. So here in our base scenario, we have all of our output information. If I wanted to create an exact copy, I can right-click the scenario, create a child, and now we have an exact copy of our parent scenario, of this base scenario. Again, it has all of the same output information. It's the exact same model. However, we can modify this however we want. I could add a completely second subsystem, now exclusive to the child. And if I go back to my base scenario, again, nothing has changed. I still have all of my output information. However, any change that we make to a parent scenario will permeate down to the child scenario. So let's say I need to add something to this parent case. If we go back to our child, here we can see it's also inherited that change. The same thing will happen if we modify any parameters. So if we clear out the objects, let's say instead of J3 at 0 bar G, it needed to be at 10 bar G. Then if I go back to my child scenario, I can see that it's inherited that change. So for our case, let's do a comparison with our control valve that we were sizing for this specific case. And in our child scenario, we'll replace this control valve with an orifice. If I hold control and drop the object on top of another, it'll morph it from one into the other. And now here in this orifice, I can specify our diameter, which was 4.510 centimeters. And here we'll specify a discharge coefficient of 0.6. So again, everything else related to the model is the same. We've only changed this orifice. If I rerun this model and I've sized this orifice properly, I can see we're still achieving that same 2 kg/s that we were sizing for. So this is a way to, again, use scenarios to quickly validate this calculation. And now if I were to make any other changes to my model, maybe if I got the downstream conditions incorrect, but we've already built and installed this orifice, I can make that change to my 10 bar G. And if I rerun my model, I'll see I'm no longer achieving that 2 kg/s that we designed for. So scenarios are very powerful. One way that I like to think of scenarios is the more that you lean into it, the more that you get from it. All of it is organized all in a single model file, so you'll only have to manage one file on your drive. But again, if you're testing different operating cases, modifying the system in any way, or doing a sensitivity analysis, you can compare that input and results very easily. Again, there's no limits on what can be changed in a scenario. The sky's the limit. You can create any modification to your model that you like. Here's some different tools to help you manage your scenarios. Again, this is more for awareness, not necessarily a demonstration. The scenario comparison tool, this will identify differences between scenarios. So as your trees get more and more complex, this is one way you can check, what did I change in each of these cases? What am I assessing? You can save individual scenarios to a file. So maybe you have this complex tree and you want to isolate a file as the final model or the final report that you're submitting to a client. You can isolate those scenarios, and you can also batch run your scenarios. So if you do sensitivity analysis, if you create all of these different cases, you can then run them sequentially, so you don't have to babysit the solver, run one model, wait for it to finish, run the next one. If you want to analyze scenarios, again, we've touched on quite a few of these throughout the webinar. You can use multi-scenario output, showing the results from each of those scenario cases. You can graph the results from multiple scenarios, both for compressor versus system curves, and then also profile graphs, as we saw. And you can also use Excel export to automate extraction to a spreadsheet, again, for comparison of those scenario results. To further touch on the Excel integration, we saw where we can bring Fathom information into Excel. We haven't touched on many places you can copy paste Excel data into Arrow. But there's also, again, further integration for Excel Export Manager to extract your information, or using Excel change sets to modify your parameters in a model. So that's a summary of our model analysis. Again, there's a few ways to review our output, whether it's tabular information from output, graphing the results to see how parameters change with one another in graph results, or how you can localize your reporting using workspace layers. There are quite a few different ways to customize your units or the parameters that you're reporting to personalize your report. And then also we saw how scenarios are a framework to evaluate your different design alternatives. So whether that be a different operating case, a existing system versus an expansion, again, anything that you want to change in a model, you can very quickly create a child scenario, make that modification, and not worry about ruining any of your work. Then finally, there's a lot of ways to play nicely with Excel. We saw a lot of ways to copy paste information from AFT Arrow into Excel. And then you can also automate that process using the Excel Export Manager, or going the other way, you can use Excel to mass modify your models. So that's everything from a model building and model analysis perspective. Now we're going to touch on some odds and ends very briefly, and then touch on some additional resources as you get further and further into learning the software and building your models. So the first thing we'll touch on is heat transfer. So we can model things from thermal mixing. Let's say you have temperature streams of different, or fluid streams of different temperatures. It can calculate what's your final resulting mixture temperature. There's quite a few different options for heat exchangers. These can be more theoretical, maybe a controlled temperature or specifying heat rate, or even a rise in enthalpy. Or you can actually model the heat exchanger itself, following different correlations for counterflow, crossflow, parallel, shell and tube heat exchangers, things of that nature. If you wanted to, you could model both sides of a heat exchanger and link them thermally. That would use both the hydraulics of the system, of how much flow am I getting through each of these pipes, as well as their inlet temperature conditions to determine the heat transfer rate. Then finally, you can also consider ambient heat transfer. So if you have your very large piping network, determining how much insulation do you need on your pipes to meet different standards or to avoid condensation, or in the case of pipes out in the sun, how do you make sure that you're accounting for that ambient heat rate or that heat flux from the sun shining on your piping. So it'll create a resistance network, again, considering the internal conduction through the pipe material, through any insulation, and then obviously the external convection effects as well. In terms of compressible flow, heat transfer can be much more dramatic than in incompressible flow. And again, it's that constant interaction between velocity and flow rate and pressure drop. All of that's also dependent on your temperature. So here, if you are heating up the fluid, you'll get a different velocity compared to if you're cooling it down. And obviously, the more temperature you're adding, the less dense your fluid. Whereas if you're cooling it down, generally the less or the more dense and lower velocity you would see. You can also see in adiabatic, you'll see a temperature change, again, from the Joule-Thomson effect from the actual fluid properties directly. The other odd and end we'll touch on is sonic choking, which in our model, we can see here our output. And here in this scenario, we are not sonically choking, but here we can see junction 3 is downstream of the sonic choke point. However, our model still runs. We're still able to determine things like our pressure and velocities throughout the system. Again, a very brief overview, probably not doing sonic choking its full justice, touching on just this odd and end section. But sonic choking occurs when the local velocity of the gas exceeds the sonic speed. You may remember speed of sound and air, I believe it's 343 meters per second. So if you are flowing your gas or air in your model faster than that, you've achieved that speed limit and it can no longer increase flow beyond that velocity. So we don't model supersonic flow. You can't model a converging and diverging nozzle. However, it will indicate sonic choking is occurring in your system. You have this limitation on your delivery conditions. What changes do you need to make, or are you still able to meet your delivery conditions with that sonic choking in place? The big picture is when you are sonically choked, if you further reduce your downstream pressure, if you're trying to increase the amount of flow by reducing downstream pressure, that no longer is effective. You no longer generate that additional flow that you're going for. Flow can choke at 3 different geometries. Most often you learn about restriction choking, where it might be a valve or an orifice where the flow going through this reduced area has to speed up, and it may go above that sonic velocity and sonically choke. However, you can also see sonic choking at expansions, whether that be an area change or maybe you have a T that is diverging flow. You have 1 pipe coming in, 2 pipes coming out. It could sonically choke there. Or as we saw in our model, it can also sonically choke at the endpoint of a pipe. Again, we have plenty of webinars that go into sonic choking in much more detail than we can here. This more so touches on some of the things you want to be aware of as you're getting started in compressible flow analysis. Note that sonic choking can also occur multiple places in the same system. So here, if we have a tank going to an area change through an orifice and then going to this discharge tank, we can see 3 different types of choking. We can see that expansion choking at the area change where the area has increased, choking at our orifice, kind of what engineers expect, restriction choking, and then also choking at the endpoint. As the fluid gets faster and faster, there's more and more pressure loss. As we saw in that graph, the velocity will kind of exponentially increase towards the end of the pipe until it sonically chokes at the endpoint. Note that in a case like this, Arrow will still be able to model your fluid properties following a choke point. The main limitation is endpoint choking, where we can't determine what are the properties directly downstream of the sonic choke point. And here we can see that same analysis, but now in Arrow, where here we're graphing our Mach number, where a Mach number of 1 is sonically choked. We see that dramatic increase in velocity at our area change, a dramatic decrease. This is usually due to a temperature change instead. restriction choking, which we don't show because it's choking inside the component itself and not in the pipe. And then again, that dramatic increase in velocity as we lose more and more pressure due to friction until it sonically chokes at the end point of the system. So in a nutshell, 3 minutes of sonic choking. Hopefully it's not just enough to confuse you. Hopefully it gives you a little more insight of what you should look for if sonic choking occurs in your AFT Arrow model. So that's really everything related to building and analyzing your model. We'll touch on some add-on capabilities for AFT Arrow. You can use the goal seek and control module to automate iterative processes. So you can set things like a goal. Maybe that's a temperature that you're trying to meet at a particular point. You can set a variable, maybe the amount of flow that you're bypassing a heat exchanger through. So this collection of setting a variable to achieve a goal, you can use that for single variables, or you can use it to emulate more complex control systems, maybe indirect control for things like temperature, instead of the pressure or flow controls built into the control valve in the software. The extended time simulation module, or XTS, again uses steady state snapshots to model long transients. We can determine things like, here's the steady state mass flow. If we maintain that for 1 second, here's the amount of mass removed from the tank. Here's what the new tank conditions would be. And we can run that over and over to, again, approximate those long transient events. The automated network sizing module will test different pipe diameters to, 1, achieve your design requirements. Maybe you have maximum velocities or supply conditions you have to meet, but it can test different pipe diameters to then minimize things like weight, capital cost, or justify a larger pipe to minimize life cycle costs. Maybe a larger pipe creates a less resistance. Your compressors and your other equipment doesn't have to work as hard. You save that energy over the life cycle of your system. So I'd also like to touch on some of the other AFT offerings, especially if this is your first experience looking at AFT. So today we looked at AFT Arrow, which is our gas and steam modeling at steady state, and we touched on our slow transient analysis. We also offer what's called rapid transients. So that could be, how does your system respond to very quick valve closures or relief valves opening? How are those pressure waves going to transmit through your system, and can also impact the transient forces on your piping. So we have all of those offerings for gas and steam, and then we have complementary offerings for liquids. So liquid steady state, liquid transients, water hammer and surge, and then also pulsation analysis from reciprocating equipment or other pulsation sources like cavitation collapse, for example. If you're looking to learn more, I'd recommend going through our quick start videos or our quick start guides. It's a much more structured approach to building, defining, and analyzing your model. Again, it'll go through a lot of the same information we went through today: the status light, the highlighting, fluids, adding junctions, what's output, what's graph results. Again, in a much tighter format, especially valuable if you are going to be training other junior engineers in how to use the software. Those can be found from our website. And if you like webinars, which I imagine you do if you've lasted through this entire webinar, we do host webinars twice a month that are live, and you can always access our backlog from our website or from our YouTube channel. Typically, they're targeted more educational than just how to use the software. So trying to understand things like check valve slam or the basics of pumps, running them in parallel or in series, non-Newtonian fluids. Again, because our software runs the gamut across all different fluid modeling approaches, we have to have a foot in a lot of different analysis styles. Documentation is also a very good resource if you're looking for things like examples or the underlying equations of how we're approaching a problem. You can go to docs.aft.com, select the relevant product, and all of that information is available on the web for you to access. There's plenty of other resources we could get into. The kind of most valuable one, I would say, is our 2-day training seminar that we host 3 times per year. You can always sign up, come out to our office in Colorado Springs, and we'll go through everything in detail that AFT Arrow can offer. Obviously going also into the theory, like how is sonic choking approached, what is sonic choking from a theoretical perspective, relief valves, equipment sizing, building your models, heat transfer, and again, really running the gamut of our full application. We publish blogs once a month, contribute to other technical papers and conferences, and again, all of this information can be found on our website. So if you're looking to learn more, and you're very ambitious and have the drive to teach yourself, we have those resources for you to reference. Sometimes it may be too much for you to take on your own. All of our licenses include engineering support, where you can contact our support team of engineers based either in the US or local to your region if you're watching internationally. We also sell what's called Flow Expert packages, where you can purchase a number of hours to work directly with an AFT engineer. That goes beyond the kind of typical engineering support questions, looking at drawings potentially, kind of collaborating and thinking about what's the best way to approach modeling a specific component or system. And then finally, we also offer consulting if you want to take your problem, package it up, and have us do it for you. We would do that through what's called the Purple Mountain Technology Group. That's a sister company to AFT, often with emphasis more on water hammer analysis. So that escalates it to building models, performing the analysis, providing a report and model, and more formal engineering recommendations. Obviously, it's a lot of content, and thank you to everyone if you've stuck around for this long. Usually they're supposed to be an hour, but given the context and how much information is kind of shown to the user in an introduction, hopefully you found it valuable. Hopefully you've learned some new skills as well. So AFT Arrow is a steady state compressible internal flow analysis tool for piping or for ducting systems. However, we also have offerings for liquids and transient flow. And a lot of what we learned today is going to translate immediately to those other products as well, as stated in this bullet point. Typically, you want to consider the modeling process in two parts. We saw model building using workspace and model data for our input and validating our specifications. Again, a common saying is garbage in equals garbage out, so your results are only as good as the information put into the model. The second piece was model analysis using output for tabular information, graph results for understanding how parameters might relate to one another, and then workspace layers to associate that output or input with the model itself. And as you can tell, this introduction is really only scratching the surface of Arrow's capabilities. If I could, I would talk for hours and hours about our product and get everyone perfectly trained, but there's plenty of other resources, from quick start guides for brand new users or 2-day training seminars to get more and more familiar with the software, kind of refine your process of building and analyzing a model, and then hopefully use it as a skill that you can carry with you throughout your entire career. Especially if you've made it to the end, I'd like to thank you for attending. If you have any questions that we didn't answer during the webinar, feel free to email them to webinars@aft.com. And again, we do these webinars twice a month, sometimes more. So if you have an idea for a future topic, you can always submit a topic to webinars@aft.com. Again, my name is Nick Vastine, a business applications engineer with Applied Flow Technology, and we look forward to having you in another AFT webinar, hopefully sometime soon. Thanks again.